Hello everyone, and welcome to the Torque Lab. Today we are going to test the second condition of equilibrium. The second condition of equilibrium states that for an object in equilibrium, the sum of all of the torques must be zero, or the positive torques must equal the negative torques, or the left-hand torques must equal the right-hand torques, or the clockwise torques must equal the counterclockwise torques. Today we're going to take a small half-meter stick and apply a variety of torques to the right and to the left. And we will show that within a couple of percent every time we do this, the left torques and the right torques are exactly the same. Let's take time out to take a look at the apparatus. Right now, we are looking at the left end of the apparatus that we are using to validate the second condition of equilibrium. We can see that a bracket is placed here and it is positioned precisely at the 1.00 centimeter mark. Hanging on it is a 50-gram weight. The total mass on the left is therefore 68.5 grams. Positioned on the right, we have a 100-gram mass, and this has been moved back and forth so that it has precisely balanced, and we see that the throat of the C formed by the bracket is at exactly the 39 centimeter mark, so that the entire apparatus is now balanced. We can see when we move out that it's nothing more than a seesaw with the weight on the left, the weight on the right, and the fulcrum in the middle. In order to guarantee that the force of gravity on the stick has no effect, it was very carefully moved back and forth until the apparatus balanced without the outside weights on it. And in this particular case, if you look very carefully, you can see that inside at the throat of the C, it is positioned precisely for this particular meter stick at 25.00 centimeters. Some meter sticks do not have their center of gravity right in the middle because wood is not exactly uniform. So gravity produces no torque because the center of gravity is right above the fulcrum. The fulcrum produces no torque because it is at the pivot. We obtain the torque on the left by finding the force equal to the weight of the left mass and hanger times the distance between the left hanger and the fulcrum position. We multiply this distance by the weight of the hanger, and that produces the left torque. Likewise, for the right torque, we find the distance from the fulcrum position to the position of the hanger, and we multiply that by the weight of the hanger and the weight, and the result of that is the right torque. If the second condition of equilibrium is true, we will find that for a variety of positions on the left and the right, when we calculate the left torque and the right torque, within experimental error, within a couple percent, we will always get the same values. Now that we've seen the apparatus, let's take a look at the data that is given to you in the Torque Lab handout. In the handout, on the front page, you will see a table like this. I have only shown the first line. You notice in the first column the numbers 1 through 7, and again the numbers 1 through 7. These are the positions we placed the left hanger. We placed it at exactly the 1 centimeter mark, then the 2, 3, 4, 5, 6, 7, and so forth. For the first 7 lines, we used a 50-gram mass. on the right side, we always used a 100 gram mass. Once we positioned the mass on the left side, we adjusted the right mass until the apparatus balanced. And then we changed the position on the left to 2 centimeters, 3 centimeters, 4, 5, 6, and 7. Each time that we did that, we readjusted the mass on the right so that we obtained precise balance. That is what the numbers are here over in this middle column. These numbers were set exactly, but the numbers in the middle were obtained by carefully balancing the apparatus. Half of a millimeter made a difference. That's why you will see that some of these numbers in the middle column are out to 5/100ths of a centimeter. It's a very, very sensitive and accurate apparatus. In the first run, we placed a total of 68.5 grams on the left. And then we put a 100 gram on the right, and then we carefully adjusted it and found that it was at the 39.00 mark. The stick was precisely balanced. So this is experimental data here. This is data that we actually set. For the first 7 runs, we had a 50 gram mass plus the mass of the hanger on the left. For the next 7 runs, we did exactly the same thing, except we added an additional 20 grams so that we had 70 grams extra here on the left, plus the mass of the hanger. And we should note that the mass of the hanger is not negligible. It is 18.5 grams. So let's take a look at how we analyze the first line. The raw data is the position of the mass. Here it's exactly, these are all 1.00, 2.00, 3.00. I don't have to write that here in the table. Then it was balanced, and this is how x right was obtained. In this case, we found that x right was 39.00 centimeters. What we want to do is show that when it's balanced, the left torque and the right torque are the same. So, to do that, we first have to calculate the left torque. First, we have to calculate how far it is from the pivot. And that is done by subtracting XL from the position of the fulcrum. Now, for this particular apparatus, the fulcrum position was exactly 25.00 centimeters. I found that if I moved it to 25.05 or 24.95, it was out of balance. It's very, very sensitive again. So exactly 25.0. To obtain the distance from the fulcrum for the left mass, we subtract the indicated position from the fulcrum position. 25 centimeters minus 1 centimeter is 24 centimeters, and that is where that 24 came from. We have to calculate the mass. We had 50 grams extra on the hanger, but the hanger has a mass of 18.5 grams. So to get the total mass, we take the extra mass we added plus the mass of the hanger to get 68.5 grams. Now, that's going to be the same for all of these first 7 runs. these are all going to be the same. For all of these 7 runs, we used a total mass of 68.5 grams. Next, we have to calculate the weight of that 68.5 grams. That is the force being applied to the meter stick. So to calculate the force, first we convert the 68.5 grams to kilograms by using dimensional analysis. Then we multiply by G, and in this case we got 0.67 newtons. That is where the left force came from, 0.67 newtons. And since the mass is not changing, this is not going to change for these 7 runs either. So this column is going to be the same for the first 7 runs, and so is this column. What about the torque? Well, now that we know the force on the left, and we have calculated the distance from the pivot, we multiply the force times the distance from the pivot, and we get the torque. In this case, it evaluates to 16.1 Newton centimeters. No need to always convert torques to Newton meters unless you're combining them with other things. For this experiment, we're going to use centimeters. So we are applying a 16.1 Newton centimeter torque for this first run. These torques are going to change for all 7 runs because the distance here is going to change for these first 7 runs. So the mass and the force columns will be the same throughout, but the distance to the pivot will change, and of course the torque will change. So in this case, we applied a torque on the left side of 16.1 Newton centimeters. We then, as I said, adjusted the position of the right mass until it balanced. And that's what's recorded in this column here. In this case, 39.00 centimeters. Incredibly, if I moved it half of a millimeter, it was out of balance. Or if I decreased it half a millimeter, it was out of balance. We have to calculate the distance of the right mass from the fulcrum. Because it's to the right, and the numbers on the meter stick increase to the right, we calculate the right distance by subtracting the fulcrum position from our measured position of x right. 39.00 centimeters minus 25 centimeters is 14 centimeters. And that is where that figure came from. And as you can imagine, I'm going to want to see sample calculations. The mass on the right. We keep a 100-gram mass for convenience on the right for all of the runs. We could have put more mass on the right and done another 7 or 14 runs, but after a while, it just gets to be repetitious. 100 grams is not the total mass on the right. You must add the mass of the hanger. So the mass on the right is 100 grams plus 18.5 is 118.5 grams. And that's where this came from. The force on the right is the weight of that mass. So we take 118.5 grams, we convert it to kilograms, we multiply by the acceleration due to gravity, and we get 1.16 newtons. Again, since we are going to keep the same mass on the right throughout the entire lab, all of these values, all the way down for all 14 runs, are going to be the same. Nonetheless, I'm going to want to see a sample calculation in your sample calculation showing how you calculated the left mass and the left force and the right mass and the right force. I'm going to want to see this calculation and this calculation here, but I only need to see it once. I don't need to see it more than once because these are going to stay the same throughout. Later, we're going to add 20 grams and this will increase, and you'll have to show that sample calculation too. All right. Now we calculate the torque produced by the mass on the right when we balanced it. Well, that's equal to the force on the right times the distance of that from the pivot. So we multiply dr, which is 14 centimeters, and 1.16 newtons. And when we multiply those together, we get 16.2 Newton centimeters here on the right for the right torque. Now, if the second condition of equilibrium is true, the right torque should equal the left torque within experimental error. Well, here's the right torque, and here's the left torque. I've got an arrow here connecting them. I would say that within experimental error, 16.1 Newton centimeters is about the same as 16.2 Newton centimeters. But what we do in this course is we quantify that difference. So to calculate the percent difference between the two, we take the torque for the right and we subtract from it the left torque. The convention we're going to use is, for the calculating the percent, is it's the right torque minus the left torque, all divided by the left torque times 100%. And when I did this, I got a 0.6% difference between these two torques. And that is where we got this column over here. So at least for the first run, the two torques are in fact the same, at least within about 0.6%. Now, your job is to repeat this for all of the other 13 runs that I painstakingly did. The difference down here is that for those that are done here, we add another 20 grams to the left hanger. And that makes the extra mass 70 grams. And so you're going to have to take 70 grams and add to it 18.5 grams, and you'll get 88.5 grams for the left mass. You'll need to show that sample calculation. I need to see this sample calculation for the mass. I need this sample calculation, and I need this one again when we've added the 20 grams. In other words, these are going to turn out to be 88.5 grams. But I want you to show that in the sample calculation. I want you to show all of this work, I would say, for 3 runs. Show all of this work for the next run here with 68.5 grams. And of course, you've got to do all the work for the rest of it. And then I want to see this done for the heavier mass on the left for XL equals 1 and 2 centimeters. So I want to see nicely laid out. I don't just want a piece of paper with a bunch of stuff on it. You can block that thing out somehow on the report here. I would suppose that you could cut this area here nicely, either in vertical thirds or horizontal thirds, and show all of the calculations you need. Show all of this for the second run, and then show all of that for the first 2 runs with a total of 88.5 grams on the left. If you do the calculations properly, you should get exactly the same results that I got, because we're all using the same data. And you will find that the percent deviations here are all typically less than 1.5%, or even in several cases less than 1%. And then you can draw your conclusions. If we see that for all of these different runs, we're doing a total of 14 of them here, that in every case, the percent difference between the left and right torque is a small percent, then that means within experimental error, the left torques are equaling the right torques when it's balanced, and as a result, the second condition of equilibrium is validated. Good luck.